talked about relations. Now, a specific kind of relation is a function. What is a function? Well, great question. A function is a rule that assigns each input, meaning x value, to exactly one output, meaning the y value. In other words, a function is a relation where x's cannot repeat, but y's can. So the first thing we want to learn is how can we tell if something is a function or not? So if you have an ordered pair, or a list of ordered pairs like this, or a table, if any value of x repeats, it is not a function. If every value of x is unique, or every value of x is different, then it is a function. So in ordered pairs, I only have to look at the x values. The y values can do whatever they want, but the x values have to all be different. So I would say, yes, this is a function. And the reason is all x values are unique. Or you could say all x values are different. Now as I look at this one, I see I have this x value, this x value. Look right here. So this is not a function because the x values do repeat. So x equals 6 repeats. That's the reason it's not a function. Okay, now for the table, it's the exact same process. We look and we say, okay, I need to look at the x's, so I only have to look at this row. All of those are different, -1, 0, 1, and 2. So yes, that's a function. And again, the reason is because all x's are unique. So that's how you tell if a list of ordered pairs or a table is a function. All of these we're looking at are relations. This is a relation, this is a relation, this is a relation. There's not any restrictions on relations. Relations are just any combination of ordered pairs. It can be 3 of them, it can be 4 of them, it can be an infinite amount of them. So relations have no restrictions. They just are any set of ordered pairs, whether it's a pair or a lot more. But functions have this limit. So now that we know how to find out if it's a function when it's an ordered pair or a table, need to fix that typo right there. Ordered pair. Oops. Okay, now let's look at mappings. So I don't know if you've seen mappings before or not, but they look like this. So this is an ordered pair right here. This is the ordered pair -3, 5. This is the ordered pair 0, 7, and 1, 3. So it just draws an arrow. It may not be easy to see, but these are arrows, not just lines. You get the idea. And it starts the arrow at the x value and draws over to the y value. So here, if any of x value has more than one arrow coming from it, it is not a function. So we look, -3, we're only having to focus here. The domain is the x values. So this has just one arrow, that's good. Just one arrow, just one arrow. So yes, it's a function. Because we look here, we see there are 2 arrows pointing to -3, but that's in the range, that's a y value. And y values are allowed to repeat. It's fine for a y value to show up more than once, just x's can't show up more than once. So we look at all the x's, -2, 1 arrow, 0, 1 arrow, 3, 1 arrow, 4, 1 arrow. So yes, this is also a function. Okay, but we look here, we see the problem. There are 2 arrows coming from -3. So that really means this gets repeated, because -3 is in the ordered pair -3, -2. It's also in the ordered pair -3, 0. So no, this is not a function, because that -3 has more than one arrow coming from it. Okay, equations. The best way to figure out if an equation is a function is basically to say all equations are functions unless there is no y at all, if there's no y that shows up, or if the y has an exponent. Now, I could more formally say if it has an exponent other than 1, because, for example, this is a function. Technically, this y does have an exponent because the understood 1, but that's fine. You can have an exponent of 1. You can have the understood 1. So this one is a function because there is a y. That's requirement number 1. And its exponent is just the understood 1. So this is a function. But this is not, because this y, while we do have a y, it meets the first requirement. It doesn't meet the second requirement. It has an exponent that's not 1. It has an exponent of 2. So that's why this is not a function. And finally, with graphs, we use something called the vertical line test. It says if any vertical line you could draw goes through the curve of the line and touches it at more than 1 point, it is not a function. So, for example, if I just draw several vertical lines, I'm not drawing them in any particular spot, I'm just trying to show you what we're talking about. Now, all of these vertical lines do touch the curve, but this vertical line only touches it in one spot. This vertical line only touches it in one spot. Same with this vertical line, and so on. So since every vertical line we could possibly draw only touches the graph one time, this is a function. It passes the vertical line test. So if every vertical line touches just once, it passes the vertical line test, which, by the way, you're welcome to abbreviate this VLT. Even textbooks will do that, and mathematicians. So this is a commonly used abbreviation, VLT, but do it in all caps, VLT. Another way people do it is they say, okay, if I just hold my pencil or my pen upright so it's vertical as far as that graph's concerned, I just move it across and say, okay, is this ever going to be hitting the graph in more than 1 point at a time? This passes. Okay, now as we look at number 2, okay, this vertical line, that would touch in just 1 point. But once I go farther over, this touches it in way more than 1 point. This touches it in 3 points. Now I could keep drawing more of them and show that it does it in lots of places, but if you even have one line that hits more than 1 point, that means the answer is no. It fails the vertical line test, because a vertical line, at least one of them, touches the graph in more than 1 point. So since this vertical line touches the graph in more than 1 point, this is not a function. Okay, here, just 1 point, just 1 point, just 1 point, just 1 point, just 1 point. So the real tricky spot is right here. So it's on the y-axis. You can see this makes what's called a jump, because it goes from being down here at -2 to up here at +2. But this does not hit it in 2 points. It does hit it right here in this point, because that circle is closed, meaning it's filled in. So the graph does exist there. This open circle means the graph goes all the way up to that point but never reaches it. So this one really does touch in just one spot. It touches right here, because up here, that open circle that's not filled in means the graph doesn't exist up there. So this one is a function also. Now, if you've got the paper in front of you, I encourage you to try some on your own. Press pause and try some of these on your own, and then see if you're correct once you come back. So number 4, if I use the pencil test, I know mine's a pen, but if we go across, we see, we are hitting more than 1 point at a time. You can see I'm hitting it up here and down here. So if it helps you to draw the vertical line, you certainly can. You don't have to draw these. If you can see it, that's fine. So this is not a vertical line. It fails the vertical line test. Okay, this one, I'm only ever touching it 1 point at a time. I'm never touching it more than 1 point. So this is a function. Okay, same here. If you move something across, this only ever touches 1 point at a time. I know this can be hard to see when you have something as thick as a pen or a pencil, so if it helps you to draw the vertical lines, by all means do that. Now I know it's hard to tell exactly if it hits more than one spot when it gets really steep, but you don't really need to worry about that. When it's curved like this, you can assume, even when it gets really steep, a vertical line will hit it at just 1 point. So just 1 point, 1 point, 1 point, 1 point. So this is a function. We have a horizontal line here, but no matter where I draw a vertical line, it would only hit it in 1 point. So this also is a function. In fact, it turns out every straight line, except for one kind, is a function. So ones that are slanted this way, ones that are slanted that way, ones that are horizontal, all of them will be functions. However, we see here the one type that is not a function, and that's when it's a vertical line. Because a vertical line, if I draw a vertical line through this, I'm hitting every single point on this line. I don't miss a one. I'm hitting an infinite number of points. A vertical line would hit this everywhere it exists. So that is not a function. It fails the vertical line test. So every straight line, except for vertical lines, is a function. So given that, you should know 9, yep, that is a function. It's a straight line, and it's not vertical, so it would pass the vertical line test. It is a function. Okay, now switching gears a little bit. We just talked in the previous part about how to figure out if something is or is not a function, whether it's ordered pairs, graphs, equations, mappings, or tables. Now we're going to talk about function notation. So first of all, the word notation just means how we write things. So notation is just a big word, and it means how we write stuff. So you, in your math career so far, have more often used this form for an equation. Y equals whatever with x and some numbers. With function notation, when you're writing it as a function, instead of y, you use f of x. Now, this is said f of x. It's going to sound like I'm just talking some math nonsense, but it'd be really good to listen right now. This is not multiplying. If I wasn't afraid of scaring you over the internet, I would shout it and tell you it is not multiplying. This is not f times x. Now I understand that's confusing because most of the time when there's parentheses, that means you multiply. I agree with you. I don't know exactly why they came up with this kind of notation to write stuff, but this is what they're saying. We have a function, and they've given the function a name. This function is named f, and the variable that it uses is x. So that's why they have two letters. One is giving the function a name, f. The other is telling you what variable the function uses, in this case x. So this is, you don't have to say this long, but it's the function named f whose variable is x, or just f of x, a function of x. But what's important to understand here is that just like y is one single variable, so is this whole thing. F of x is just one variable because y and f of x are interchangeable. So I know this looks a lot different, but it means the exact same thing as y. So x is the input, f of x is the output. So one thing you need to know how to do is when they give you a function in function notation where it says f of x, then they might ask you to find f of 3. So what they're asking you to do is instead of putting x in the function, replace that x with a 3. So it's like they're substituting 3 in for the x. So instead of saying f of x, we say f of 3. So we just rewrite this equation and we plug 3 in for the x. Then I simplify. Negative 4 times 3 is negative 12. Negative 12 plus 7 is negative 5. So whatever's in parentheses, plug it in for the variable. I'm going to write that down. I think that's worth remembering. Whatever is in the parentheses, plug it in. Okay, so on B, we see what's inside the parentheses is negative 2. So I do negative 4, I replace the x with negative 2, plus 7. I'm gonna get some color here to help hopefully make this make sense. So f of negative 2, I just wrote that part right here. I'm not dividing, I'm just underlining. So f of negative 2 means take the function and plug negative 2 in for the x. Now they have something extra here. That's this plus 3. So this is saying take the function with negative 2 plugged in, which we have, and then add 3 to that. So this is a separate piece. This doesn't go inside the function because it's not inside the parentheses. Only what's in the parentheses gets plugged in for x. This is just something extra we tack onto the end. So negative 4 times negative 2 is positive 8. 8 plus 7 is 15. 15 plus 3 is 18. So I put these two examples here to make sure you see a difference. Here, the plus 3, the number added, was outside the parentheses, so it just went in as a separate piece after I did the whole function. However, here the plus number, the plus 2, is inside the parentheses. So that means I'm going to replace all of x with r plus 2. So I replace the x value right here with r plus 2. Now we have to distribute, because r plus 2 doesn't go together. They're not like terms. So I do negative 4 times r, and then negative 4 times 2, which gives me negative 8. And then don't forget the plus 7, which the plus 7 is just coming from right here. So negative 4r stays that way because there's no other r. Negative 8 plus 7 is negative 1. Okay, now there's a lot of practice with these, but I want to make sure I hammered this home best I can. So see, this one they named the function h. And instead of using x as their variable, they use t as their variable. So this time, we plug 1 in for t. Now notice, t shows up twice. So I plug in 1 both times it shows up. So I plug in 1 for this t, I plug in 1 for this t. 1 squared is 1. 1 squared is 1. 1 times 2 is 2. 4 times 1 is 4. And I have the minus 5. 2 plus 4 is 6. 6 minus 5 is 1. This may seem strange because we have a letter inside. Of course, we did that by key, so maybe it's not too bad. But we go back to this. Whatever is in the parentheses, plug it in. So this time we're going to replace the t's with negative 3m. So I do 2 times negative 3m squared plus 4 times negative 3m minus 5. Okay, negative 3m squared. You got to remember what squared means. It means times itself. Negative 3 times negative 3 is positive 9. M times m is m squared. 4 times negative 3 is negative 12. We keep the m. Then we double this. 2 times 9 is 18. And that is as far as we can go, because none of these are like terms. We cannot combine m squared with m, or things with m that don't have an m. So that's our final answer. 18m squared minus 12m minus 5. Okay, so on this last one, notice we have this extra piece outside. So up here we have that plus 3 out to the side. This one is telling we need to double what we get when we plug 5 in for h. So 2 times, then we're going to plug 5 into the h. 2 times 5 squared plus 4 times 5 minus 5. So I have to tack on that extra 2 times in front. Okay, 5 squared is 25. 25 times 2 is 50. 4 times 5 is 20. 5 plus 20 is 70. 70 minus 5 is 65. So we get 2 times 65, which is equal to 130. Okay. Now we have a new function, different function called f. The variable is x again. So I start by plugging in -2. -7 times -2 is positive 14. 14 plus 3 is 17. So f of -2 is equal to 17. Now it says plug in 4. So I replace the x with 4. -7 times 4 is -28. -28 plus 3 is -25. Now C is pretty tricky. So first we got to make sure we plug this entire thing in for the x. So k minus 4 goes in for the x. And then after we do that, we plug in this plus 1. Okay, so first I'll plug k minus 4 in for the x. So -7 times k minus 4 plus 3. So that is the f of k minus 4, that whole thing. Then we do the plus 1, which is this extra thing added on. So I need to distribute -7 times k. -7 times -4 is plus 28. We can't combine anything with the 7k because there's no other k's. So the -7k just stays as it is. We can add all three of these together. 28 plus 3 is 31, plus 1 is 32. Now I know I've done a lot of these. If you feel like you've got it under control, by all means you can stop the video, but I'm going to do one more example. This is another that has a variable show up twice. In this one, the name of the function is g. Its variable is x. So I plug in -3 for both of these. Now, when you plug this in a calculator, you do have to put parentheses around it. If I type -3 squared in the calculator, it's going to give me -9, and that's not the right answer. Now, the calculator is not wrong per se, but the way they program calculators is when you plug in a negative sign, they treat it like it's -1 times this thing right here. So they're just following the order of operations and doing the exponent first, then applying the negative sign. But we must make sure we're squaring the entire thing, because if you plug this with parentheses in the calculator, you'll get the correct answer, which is +9. Anytime you square something, it's going to make it positive, because you're multiplying a number by itself. So it's either a positive times a positive, or here, it's negative times negative. -3 times -3 is +9. I'll treat this minus like a negative. -2 times -3 is +6, for a total of 15. Okay, here it says g of 5a. So I plug in 5a for both x's. I need to square the 5, that's 25. Square the a, that's a squared. 2 times 5 is 10, so we have 10a. Okay, this says plug b squared into g. That'll be in line with what we did over here. But we also have to make sure we multiply the whole answer by 3. So I'll do 3 parentheses. Now g of b squared, I plug b squared in for x. So I did have x squared. Now I have b squared squared minus 2 times x, so minus 2 times b squared. b to the second squared is b to the fourth, because you multiply those two exponents together. And then 2b squared is 2b squared. So our final step is to distribute the 3. Do 3 times b to the fourth. 3 times 2 is 6. And we have our final answer. So that's called evaluating functions, or finding functions at a specific value.